Welcome guys. So in this video, we just using the Gaussian curvature and see Gauss Bonnet will imply in some different surface. In this video, we only take x to be the sphere, and let's say this is radius r and the center is at origin, and we need to first compute the Gaussian curvature of the sphere. So let's parameterize this sphere by the sigma. So we have theta and phi. Okay. Actually, for sphere is very we can apply a trick to compute the Gaussian curvature. So actually, we don't need this parameterization. Okay. So it's but it's fine. Okay. So let's say E is be sigma u. So u is the first coordinate theta, and v is the second coordinate. Okay, so let's say sigma u is basically fixed r. So differentiation respect to theta. So it's cosine theta, cosine phi, cosine theta, sine phi, minus sine theta, right? So sigma u dot sigma u. Sorry, let's first compute the sigma v. So sigma v will be differentiation respect to phi, right? So it's sine theta minus sine phi, sine theta, cosine phi, and 0. Okay, so let's compute the so-called first fundamental form. Okay, so I just calculate for fun, right? Because actually we will see if we just want to compute a Gaussian curvature, then we don't need actual quantity. Okay, so sigma dot sigma u will be sigma u dot sigma u will be just r. Right, you can check because you just flip this. Okay, so if you square both, then you get r squared. And f you get 0, and g you get the r squared sine theta squared. Okay, so this is the famous form. So it's d theta squared sine squared d phi squared. Right, so this is the standard calculus results. Okay, then the next we need to calculate so-called second fundamental form, right? So second fundamental form, basically you need to first compute n. So n is the sigma u cross sigma v, sigma u, sigma v, right? But if you see the picture, right, you know that n is actually indeed a sigma divided by r. So this is exactly n, right? So you don't have to compute everything. You already get this n. Okay, so the second fundamental form L is defined to be n dot with sigma u, right? But as we prove, this is minus n u sigma u because n dot sigma u is differentiation is 0, right? It's 0, so this is just exactly minus sigma u divided by r. So it's negative e divided by r. Okay, and the same reason for the Lm and this n, right? So this n will be minus f divided by r, which is 0, and then this minus g divided by r. It's the same thing. Okay, so it's just this. Okay, so let's remind you guys the Gaussian curvature K will be ln minus m squared divided by eg minus f squared. Okay, so this is a definition of Gaussian curvature, right? So basically the second fundamental form and the first fundamental form. Okay, so but you see they are exactly the same, right? So this is just eg minus f squared, eg minus f squared, and 1 over r squared, right? Because L will actually these two matrix, right? The L is exactly minus r E, right, and this is minus r g, right, and m is 0, f is 0, so it's eg divided by eg, but there's r squared factor. Okay, so if you see this, then that means actually you don't have to compute this EFG. It's basically you can already get the k is 1 over r squared. So this is the first result. Okay, so let's kill something. Okay, so for the sphere with radius r, we just use a definition. We can get k equals 1 over r squared. By the way, actually there's a very so we use this formula to get the Gaussian curvature. And in general, you need to use this Brusaki formula. This is very complicated. Usually we will not use it. Right, but for a sphere, that it's very easy that we can get these results. Okay, so next we can apply so-called Gauss Bonnet, and see what Gauss Bonnet will give us. Okay, so there are two kinds of Gauss Bonnet. The first is global Gauss Bonnet. So the global Gauss Bonnet tell you that the total Gaussian curvature applied on all the manifold, let's say X, will be 2 pi Euler characteristic of, let's say, X. Okay. So X is just sphere now. Okay. And so if we do this, it's very easy that 1 over r squared times 4 pi r squared, right? Because this is the radius of, so this is the surface area of the sphere with radius r. So get 2 pi equals 2 pi chi of x squared. So we get chi of x squared is 2. Okay, I think this is everyone knows about it, right? Because you can just triangulate the sphere, then it counts the Euler characteristic by counting the edge. The edge minus the vertex is plus face minus edge. Then you can see whether it's 2. If you cut cut this one and this one, cut 2 equators, then you can count. Maybe let's count it. I think there are 4 faces. Let's say we have 1, 2, 3, 4, 5, 6. So 6 vertices. Let's see. Oh, sorry, there's no list. So we have. Let me see. Oh, so we have 2 vertices, right? 4 face, 4 edge, right? So we get 2. Okay, so the global Gauss Bonnet just tell us the Euler characteristic. So let's see the local Gauss Bonnet. Okay, so local Gauss Bonnet will tell you what? Local Gauss Bonnet say that if you have a triangle or something that maybe not triangle, then the geodesic curvature along with this S. So usually we will let this term vanish with the KDA. So the KDA now is the area enclosed by this triangle will be I think plus the turning angle, right? So the turning angle. So turning angle means that suppose you are some people walking this way and then you change your directions. And this is turning angle. So turning angle will be 2 pi. Right. So this is the Gauss Bonnet. And we can use this to prove the famous result that if you cut the triangle on the sphere then you will get the this area, right? Let's say this area is A. Then you can prove that if that A divided by r squared will equals to alpha plus beta plus gamma minus pi. So this is very famous result. Means that the angle of this, the sum of this angle of these 3 triangles will exactly give you how curved the space. So at least for sphere. Okay, so we can prove this fact by the local Gauss Bonnet. Okay, so let's prove it. So since we are working the geodesic, right, there's no this term. In the case 1 over r squared times our A, so this area is A, right? Plus the turning angle. So turning angle means that so this is state theta 1, right? But alpha is pi minus c, so this is pi minus theta 1, right? So we get pi 3 pi minus theta 1 minus alpha minus beta minus gamma. So you see this is maybe this is theta 1, theta 2, theta 3. Okay, so let's making it clear. Okay, so 3 pi minus alpha beta minus alpha minus beta minus gamma equals to 2 pi. Okay, so we get a over r squared equals to alpha plus gamma minus pi. Okay, so this is the famous Gauss results, right? If basically you just draw any triangle on the sphere, then you can check that the sum of the angle minus pi will give you the area. So the easy example is that we take r equals to 1, and then we draw the, right, this is xyz, and then we draw the 90 degree, right? You see here, here, right? So, and the radius is 1. Then you see this is the equilateral triangle, and now all the angle sum is the 270 degree, basically just 3 pi over 2. Okay, so it's easy to check 3 pi over 2 minus this area. So this area is the 1 over 8 4 pi, right? So 4 pi is the total surface area, so it's pi over 2. Pi over 2 is exactly pi, right? So this formula work, right? This area is pi over 2, and exactly is 3 pi divided by 2 divided minus pi. Okay, so easy example. So I think for the sphere, the Gaussian. So for the sphere, the Gaussian. So the key point is that for sphere, the Gaussian curvature is exactly 1 over r squared, and then this result is very beautiful and very easy. Okay, because this is the homogeneous space. Okay, so next time we can go to compute the torus, and then we can see what's other application of the Gauss Bonnet theorem. Okay, I will see you guys in the next videos. Be sure to subscribe to my channel.